Today we're going to talk a bit about the area under a curved line. This will be a little bit different than some of the other videos in that it's not going to be filled with examples or anything like that. Basically, I'm going to step through one process. And there's not going to be a lot of work attached with this. This one I really just want people to kind of take it in, what we're talking about here. So, if people think back a little bit to their physics, if you had a velocity versus time set of information. Lovely straight lines there. Oh, and back in the day, we would have had straight lines, something like this. There are different pieces of information we could take out about this. We could read velocity directly off the graph. We could find acceleration from the slope. And this, by the way, is the sort of thinking that led us into talking about derivatives. But there was one other piece of information we could take from this as well. If we started to look at the area under the line, that led us to displacement. Find displacement from the area under the curve. And I use curve in this sense to speak about any sort of functional line, as opposed to necessarily something that's not straight or crooked or anything like that. However, as I mentioned before, these straight lines are not necessarily all that physical. If you actually moved in a manner like this, you would feel the motion be very jerky and unnatural, because normally you would see changes in velocity happen in a bit smoother curve, unless you ran into something like that. So we've spent a lot of time talking about derivatives, rates of change, and how those tie into things, and that is probably about half of the foundational basis of calculus. The other half of that is the area under curved shapes, the area under a curve. So we'll look at that now. Area under a curve, and we'll talk about a means of finding the area under a curve. And we're going to start with a pretty straightforward curve, one that you're all a bit familiar with, at least should be, is the basic quadratic y equals x squared. I'm going to give myself a nice big graph to work with here. And I'll say I'm looking at the curve y equals x squared between values of 0 and 1. On, and I'm interested up to here. My line is y equals x squared. It's x. And here's y. And I'm interested in finding out the area of this curved shape underneath the line. So, let's talk about how we might be able to do this. And I'm going to start by cutting the shape up into n different rectangles. Now, if I were to cut this section up into 4 different rectangles, each one would be 1/4 wide. If I was to cut it up into 10 different rectangles, each one would be 1/10 of a unit wide. If I cut it up into n different rectangles, each one would be 1/n wide. I'm a little congested in here, but bear with me. 1/n, 2/n, 3/n, 4/n, and on up to n minus 1/n. I've left a little bit of gap there because n is indeterminate. I don't know how big n is. I just know I'm cutting up my rectangle in my shape into that many rectangles. And when I say rectangles, I mean places that look a bit like this. And I want to stress, this is not 5 over n, at least I don't mean it to be 5 over n. This is a gap that I've put here because n is this indeterminate thing. I've just cut it up into some number of rectangles that I haven't defined as a set thing. But because I know in each shape I'm bringing my rectangle up to the line y equals x squared, that tells me how high each of these rectangles is. The first one would be 1 over n squared. The second one would be 2 over n squared. The third one, and I'm getting a little bit tight in here, 3 over n squared. The fourth one, and I'm sketching up a little bit so I can see things, 4 over n squared, and my last one at n minus 1 over n squared. So I'm going to put together the area of all these rectangles, and you're going to sit there and say, well, that's not going to give you everything you need. You're going to be missing parts here. Bear with me. Oh, there is one other piece of information we're going to need moving forward. So this is just a stated result. I'm not going to prove where this thing comes from. But if I take 1 squared plus 2 squared plus 3 squared and so on up to n squared, that is a series of squares. And it actually works out quite nicely into a simple form of n times n plus 1, and I've run out of space. I really do miss my smartboard sometimes. This works out to n times n plus 1 times 2n plus 1 all over 6. Okay, that's the thing we're going to need in a minute. So, coming back to my diagram here. The area of the rectangles. That is going to equal the width of the rectangles times their height. Now the width of each rectangle is 1 over n. The height of my first rectangle, 1 over n squared. My second rectangle has a width over n, but a height of 2 over n squared. My third one would be 1 over n times 3 over n squared. And that would carry on up to my last one, which would be 1 over n times n minus 1 over n squared. I apologize for that being a little congested there at the end. Now there's a lot here in common between all of these that I can factor out. Each one of these terms has a 1 over n in it, and it's got a 1 over n squared buried in this second part. So I can factor a 1 over n cubed out of everything, and that would give me a 1 squared from the first part, a 2 squared from that second part, a 3 squared from that second part, and so on, up to that n minus 1 squared from the last part. Now you might notice that this now looks a whole lot like this sum of squares that I've got up here. The only difference being that instead of going up to n, I go up to n minus 1. So I can replace this with this expression, just replacing my n's with n minus 1's, and I can say that this area works out to be 1 over n cubed times n minus 1 times n times 2n minus 1 over 6. Okay, I'm going to need a little bit more space to work with here. But I want to leave this result up top for us right now. Okay, and I can simplify that a little bit. I can say that the area is, if I multiply that expression in the numerator out, I would end up with, don't forget my 1 over n out front, 1 over n cubed out front, And inside there I would end up with 2n cubed minus 3n squared plus n over 6, or if I put it all together, 2n cubed minus 3n squared plus n over 6n cubed. Now, I will take this one step further, because at this point all I've done is I've worked out the area of a bunch of rectangles shoved under this line. Now what does this represent? The limit as n goes to infinity for that area. If n represents my number of rectangles, if I cram an infinite number of rectangles under this shape, what have I done? I've basically filled in this entire expression with these infinitesimally thin rectangles. So taking that infinite limit effectively fills in the entire shape. And for some reason I feel the need to shade this all in. I don't really know why, but that is what taking that infinite limit is doing. And limits we've spent a little bit of time with, so let's work this limit out. This is the same as the limit as n goes to infinity of this expression of 2n cubed minus 3n squared plus n over 6n cubed. And from our discussions before, we know that at the infinite limit, it's really only that higher order term in the top, in the numerator, that's going to dominate. So this would end up being the same as 2n cubed over 6n cubed, which works down to 1/3. So, I mean, don't panic. You're not going to have to go through this process every time you want to find an area. However, what we have shown here is that the area under the curve y equals x squared between 0 and 1 works out to be 1/3 units squared. We could work out a few things with transformations from this if we wanted to. If I wanted, for instance, the area under y equals 2x squared in this same gathering, I could just multiply this by 2. Because doubling my y values are just going to make all these rectangles twice as tall, doubling the area. However, if I wanted to go between 0 and 2, I would end up multiplying by 2 squared because of that relationship that's there. Now, I'm just going to leave this here for now. I kind of want everybody to get an idea of what this area under the curve stuff looks like before we generalize it a bit more. But I will leave you with one question to try. I'll say try to repeat the process for the area between 0 and x instead of 0 and 1. That means my n value here would be an x, and these terms would be x over n, 2x over n, 3x over n, and so on. So once again, try to repeat this process going between 0 and x instead of 0 and 1, and see what comes out. Okay. That's all I'm really going to say for now. Anybody who has been following along with this and is working on related rates right now, you'll probably still want a little bit more time to work on that, and that's fine. I just wanted to put this out here so people have seen the concept before I generalize. See where we're going. Okay, everybody, that's all I have for now. Thanks for tuning in.